Hello everyone. In our previous lecture, we have discussed about a design flow for FPGA. Today, we are going to discuss about a design flow for ASIC. So, let's first understand what is ASIC. To understand ASIC, let's also go through a couple of more terms. One important term is linear integrated circuit, or we also call it IC, integrated circuit and linear integrated circuit. So basically, integrated circuit is when number of transistors or your whole circuit is integrated onto one chip, and this is specifically called linear integrated circuit because all the transistors, all the basic component of our circuit are laid out onto the same plane. So when you say one plane, it's a 2D plane where all the transistors are placed at different positions. So this is called linear integrated circuit. And what is a transistor? Transistor is a device which has usually three inputs. For example, if you see the other passive elements like resistors, inductor, capacitor, all of them had two inputs, but transistor used to have three inputs. So the earlier transistors were, so you would have heard of these names: BJT, bipolar junction transistor, PMOS, or it's also called sometimes simple MOS. PMOS, NMOS. So and also CMOS. CMOS will have both PMOS as well as NMOS. It's a design method, not but still it's called transistor. So if any transistor will have both the components PMOS as well as NMOS, then it is called CMOS. CMOS is complementary MOS. Okay. So now these are the various type of transistors which has been invented or which has been designed in last couple of years, last 40-50 years. But today most of the designs are usually focused on to the CMOS type of transistors, which has both PMOS as well as NMOS, specifically in the digital design domain. Okay, so there is another term which is ASIC, which we have said in the starting of this lecture. ASIC is application specific integrated circuit. So an integrated circuit which we are designing for a particular application. You can also say a circuit which is being designed for a particular application is ASIC. Now by circuit here, usually it means that it's a digital circuit. A digital circuit which is designed for a particular application is called an ASIC. You also see this word integrated here. Integrated means how many transistors are put onto one particular chip. That is that also defines the scale of integration. So in small scale integration, SSI circuits, these number of transistors could be in the order of thousands and less than thousands, and in a large scale integration, when number of transistors grows beyond thousands, and when the number of transistors will be in the range of hundreds of thousands, then it will become VLSI, very large scale integration. So when you say you will hear some of the related terms like VLSI design. So that means a design which would have large scale integration involved. So that means we are focusing on a design which would eventually have more than thousands of transistors or hundreds of thousands of transistors. So when we started this course, we talked about Moore's law. So because of this Moore's law, because of this integration, increase in integration or increase in number of transistors per chip, it has gone beyond hundreds of thousand limit. So right now we have hundreds of million transistors, or some of the chip also have more than a billion transistors on one integrated circuit or one chip. So that you can also call it very ultra large scale or very large scale. You can coin all those words, but they become meaningless because VLSI itself means it's going to be very large scale. It's the scale is beyond the mm, beyond the limit of our handcrafted design. So VLSI also mean that there has to be some sort of automation which should be there, so that the number of transistors could be fitted in onto chip and could be designed. So in today's lecture we will briefly go through this process of automation so that a VLSI design could be feasible, particularly the digital design. So now when we have seen in this particular course, we were talking only and only about the gates, not the transistors. We were talking about basic gates like AND gate, OR gate and NOT gate, and we also talked about universal gates like NAND gate and NOR gate. And then we have also designed various blocks which were including which were designed using these gates, and then those could be utilized to design something else. So for example, we have predominantly used multiplexers or flip-flops, and using multiplexers, flip-flop and adders we have designed further more sophisticated circuits. So but we have not talked about transistors. So who will design the transistor? That's a one question which will come in our mind, that who will design the transistor so that our digital design could be successful. So the answer to this question is usually it is designed by custom design engineers or analog design engineers, not the digital design engineers. We assume that in our digital design, we assume that these gates are available to us. Somebody has designed it. So when somebody has designed, so possibly they have designed it and they have created a sort of library, and this library is taken or assumed as an input. Okay, so what would be there in that library? See, in that library there could be you can also say there could be only one gate, universal NAND gate, but no, because of we would like to optimize our design for area. Sometime we would like to optimize our design for performance or power. Because of that, various variants of each and every gate would be there. For example, if there is a NAND gate, there would be a different design for 2 input NAND gate, 3 input NAND gate, 4 input NAND gate. And similarly for AND and OR gates also there would be multiple designs. Further, because it's going to be designed by custom design engineers and analog design engineers, they will also think about what would be the load. So basically one output of the gate, if it is going to multiple different gates, then it should be able to take care of the load capacitance. It should be able to take care of the fan out capacitance or fan out effect of fan out. So to take care of the effect of fan out, our design of the gate also need to be modified so that it can still be high performance. So sometimes multiple variants of the gates would be designed based on the circumstance, that if it is to be used used in a case of high fan out, then there would be internal design would be different, slightly different. Okay, so when the standard this is called standard cell library. Standard cells, what is standard here? So internally there is some physical dimensions like height of the gate. Physical height of the gate is fixed, that's why it's called standard cell. So if the standard cell library is the input, so basically what do we mean when we say standard cell library is the input? So it means that whenever digital design would take place, some of the estimation has to take place. Yesterday we have talked about that after placement and routing we clearly know what is going to be the delay, what is going to be the effect on the latencies, etc. So all those latencies will come because the standard cell libraries are assumed as an input, and because they are assumed as an input, so there is some characterization which is involved. So for example, electrical characterization, which means that for a particular gate what is the average delay. Characterization will also involve, it will clearly tell what is the delay when output will go from high to low. What would be the delay when output will go from low to high. Similarly, what would be the power consumption in each and every case? What is going to be the area? What is going to be the output capacitance, tray capacitance? all those electrical details are present to us in some abstracted manner, so that whenever we analyze using the standard cell library, using this particular, assuming this input, then we can have some estimation that what is going to be the overall latency, or what is going to be the minimum or maximum latency for our design, so that we can calculate clock period, so that we can say that in one clock period how much design could be fit in. So all those information is required, so that we can choose, so that we can design our final circuit. So this is the detail which is required. Electrical characterization is the detail which is required so that we can design at our gate level. But to move forward, the physical characterization, physical detail is also required, that what is the layout and what are the details about each and every layer. So what are these layers, layout, etc., we'll talk in couple of minutes. Okay, so we'll also take some example of standard cell library. So before that, I'll tell you that there is a couple of libraries, standard cell libraries, which are present. So some of them are free and open source. All these libraries also depends on that which technology we are working in. So these technologies refer to the fabrication technology. So you might have heard that 20 nanometer, 45 nanometer, or 90 nanometer. So these are all fabrication technologies. Lower technology means more transistors could fit in, and it also means that a lower technology node, basically the latest technology node, let's say 22 nanometer or 14 nanometer, it would have lesser delay. It would also consume lesser power. So and it would also be able to integrate more number of transistors per mm square, or per area, per unit area. So earlier, like 20 years back, there were many free and open source technology libraries, like Tenor, VTVT, or Illinois Institute of Technology have published their own open source library. OSU is another university which has published their own open source library. So there are various open source standard cell libraries that has been published over internet, and we can access them, and the access is required so that we can have a complete design flow for digital design. But the challenge with most of these technologies, most of these open source libraries, were that they are usually designed in for older technologies, like 180 nanometer or 350 nanometer. So basically they were at the micron level. But today we have moved on to the latest technology, which is 14 nanometer, 22 nanometer, or 45 nanometers. So for the latest technologies, we can still use the libraries which has been published by commercial companies like Cadence, Synopsys, and Mentor Graphics. So these are the three major companies in electronics design automation field, so which provide most of the software which is required for design automation. So what they don't give open source, but they give free PDK. PDK is process development kit. So this is still tied to a particular development node, like 45 nanometer or 22 nanometer, so or 90 nanometer, and then it is free in the sense that they provide all the characterization information, for example, all this information, so that we can use them in our design, and we can design our digital design or ASIC based on these libraries. So to give you some more detail, I'll share one of the document which shares the detail of these library. So this is digital standard cell library from the Synopsys. It is for 90 nanometer EDK. So when we see the detail, so a couple of things I would like to show in this detail. So one thing I would like to show is the type of standard cells available. So you see there are some 6 or 7 type of inverters which are present. You see there are some 6 or 7 type of inverters which are present. So when they say inverter x0, so that means the load is the minimum. Here it can take inverter x32 can take up to fan out of 32. So similarly inverting buffers are there. So these buffers would be able to take more load. So similarly non-inverting buffers, so which are just the so let's say one particular cell would have one particular gate has multiple fan out, so then non-inverting buffer, so that the signal will not change but it would act as a buffer. It would be able to take much more fan out. Okay, so you see in the logic gate also there are 2 input AND gates with multiple load factors, 3 input and 2 input AND gate, 3 input AND gate, 4 input AND gate. So this is also one of the reason that during the course we were kind of advocating that if the input is more than 4 input, it's going to destroy it. So because in the standard cell libraries like this, they also take at most 4 input, then after that they'll break it into multiple of the AND gates. So let's say if we would like to design a 9 input AND gate, so it would be designed using 4 input and then another 4 input and another 2 input, so or maybe 2 levels of 3 input AND gate. So similarly NAND gates are there, or NOR, XOR and XNOR. So all of these gates are available as a basic gate. Some of the complex gates are also available where AND and OR are there. So basically it takes 2 input to the AND gate and one of the input as OR gate. So this is a combination. So this will take 2 AND gate and 2 OR gate as a input. So it's a combination of gates, so that in certain cases we can directly map our circuit to these gates, and these gates are going to be much more optimized than if we use one AND gate and one OR gate. Okay, so such complex gates are also available in the standard cell library, which would help in the improvement of the performance. So some of the small decoders, multiplexers, half adders are also there. Now you see only the D flip-flop is present. You will not see JK flip-flop, RS flip-flop or T flip-flop, because but D flip-flop is present in almost different kind of variants, like D flip-flop with asynchronous reset set, with asynchronous reset set, as well as reset. So this is positive edge, similarly negative edge. So all variants of D flip-flops are present, but not the other flip-flops. Since if we have D flip-flop, we can also we can design other flip-flops also. Okay, so scanned D flip-flop is a very special type of D flip-flop which is used for sequential purpose. Now different kind of latches. In latches we have RS NAND and RS NAND type latch. So all of these other gates, pass transistors, delay lines, so these are isolation gates. These are for low power or different use cases. So that was not the purpose. Now the other thing which so once a digital standard cell library has been given as an input, it also gives basically symbols, synthesis and Verilog simulation models, HSpice netlist. So all of these things will come with the standard cell library, so it can help in the digital design, so that we can estimate area, power, etc., and we can also simulate the design. And on the second side, it can also help us in the physical compilation, which we will talk about in couple of slides. So a physical compilation view is there, report files, GSDII layout view is there, so that we can convert it into layout also. So so this is what is the meaning of physical layout. That it means that if this is the this is the overall cell that from the VDD, so from the power supply to ground, this is going to be the dimension. This is the width 1, width 2, and it is formed in the form of a grid.